So let's consider the following situation. So we have two functions. Let f of x and g of x be two functions, be continuous at x equals a. Then we're going to make the following proposition. So we have two functions which are continuous at a given point. Then first, where sum or difference is continuous at x equals a. Same goes for where product. So product of f of x and g of x is still continuous at x equals a. And the third one, where ratio, quotient, is continuous at x equals a. For quotient, we have one restriction, given that g of a is not equal to 0. So basically what this proposition is saying if we have two continuous functions, and where sum or difference is continuous, where product is continuous, and where quotient is continuous, given that g of a is not equal to 0, given that denominator is not equal to 0. So we start with nice continuous functions, we multiply, divide, add, subtract them, and we still get at the end nice continuous functions. Next proposition is about a similar statement, but about if we take composition of two continuous functions. Let f of x be continuous at x equals a, and g of x be continuous at f of a. Then g of f of x is continuous at x equals a. So basically what this statement is saying is we have two continuous functions, you take their composition, and the composition of two continuous functions is continuous. So those are two statements, and that's how we generate continuous functions from our basic ones. And basic functions are continuous. So which are our basic functions? Y equals x, continuous everywhere. Y equals x squared, continuous everywhere. Our basic trig functions, sine and cosine, continuous everywhere. Our roots, continuous if defined. So we have a nice set of functions which are continuous, and then taking their addition, subtraction, multiplication, at the end we're still going to get continuous functions. So from here we can write down the following rule of thumb. So I'm going to write down the rule of thumb. The rule of thumb goes like this. Regular functions are continuous when defined. So regular functions are continuous when defined. By regular I mean you have composition or addition or subtraction or division of regular functions, but there is nothing strange going on. You have sine, maybe cosine, you might have squares, you might have polynomials, but nothing odd is happening. There is no strangely looking function inside. For example, German, where function f of x, which is a fraction, x squared plus 3, x squared minus 9 is continuous. You look at this function and you say that's a regular rational function. It's a quotient of two polynomials. So for this function, using rule of thumb, we'll say it is continuous. The only problem that we have with this fraction is when denominator equals to 0, because we cannot divide by 0. So that is when x equals plus or minus 3. So discontinuous at this point, so continuous everywhere else, so continuous from negative infinity to negative 3, plus from negative 3 to 3, plus from 3 to plus infinity. You will either say whether it's continuous or will say whether it's discontinuous. So let me try another example on how to use the rule of thumb. Now the example will be with square root. So the same equation where continuous, and we have function f of x, now something that involving square root, say x squared minus 9. Because we have square root is defined when expression under square root should be positive or 0. So we want to have x squared minus 9 to be greater or equal to 0. So to figure out where x squared minus 9 is greater or equal to 0, what we do, we set x squared minus 9 equal to 0. We get x equals plus or minus 3. So we draw a number line, put minus 3 and 3, x squared minus 9. Pick a sample point, so we get plus, minus, plus. Now you recall what do we want from x squared minus 9. We want it to be positive, so we discard that middle interval from negative 3 to 3. So we say square root of x squared minus 9 is continuous, and we have two intervals to write down, from negative infinity to minus 3, plus from 3 to plus infinity. So I'll stop somewhere here, and we'll finish the rest of it tomorrow in class.